Hello everyone, I hope you are doing well. So in today's video, we are going to go through the 2024 VCE sample chemistry paper, part 1 of the multiple choice section. Like always guys, before I start this video, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. Just a disclaimer, these are my suggested solutions. Please let me know if you see any mistakes or have any concerns. I will have a look at them. And yeah, I just wanted to make these videos because a lot of students have been begging me to go through these solutions, because I think there isn't basically any solutions posted. So yeah, I hope this video finds you well and teaches you something, and good luck with all your chemistry studies. And yeah, let's smash through this paper. Question 1. Compared with ethanol produced from coal, the ethanol produced from sugarcane is what? Straight away, you should know. If it is produced from coal, we know it's a fossil fuel. Whereas if it's produced from sugarcane, which is a biomass, which can be basically replenished quicker, it is a biofuel. So let's look at the first one. Has a higher energy content? We can check this by going to our data book. So if I go to my data book, let's go down to what are we doing? Ethanol. If I go down to my data book, here it is. This ethanol is basically pure ethanol, like actual pure ethanol that's basically produced from fossil fuels. And it has an energy content of this. Let's write that down. So I'm going to write F, so meaning like fossil fuels. We do produce 1370 kilojoules per mole. Now, we also can actually know, because they've, if you go down, here it is, bioethanol. Let's have a look at bioethanol here. What is heat combustion? So we know it's 29.7. So from bio, it's 29.7 kilojoules per gram. All right. So let's try to compare these two. Do they have similar energy contents? Now, the big difference is one's in kilojoules per mole and the other one's kilojoules per gram. Now, it's very easy to go backwards, try to convert them to kilojoules per gram. One of the easiest way is I'm just going to convert this fossil fuel into kilojoules per gram. The way you just do it is you divide this by its molar mass. Now, what's the molar mass of ethanol? I'm just going to double check it because so ethanol is, I'm just going to go look at its formula. It's basically, okay, looking at this, we have 2 carbons, so 2 times 12, 1 oxygen, and how many, let me write that nicely down. So 1 oxygen and how many hydrogens? We have 6 hydrogens. Done. So putting this in this formula, I am able to convert that into kilojoules per gram. So 1370, 2 times 12 plus 16 plus 6. That gives me, basically simplifying all this, let me just take that out. That basically gives me 29.8 kilojoules per gram. I mean, have a look at them. They're both similar. They have actually similar energy content. So from this is wrong. A is wrong because they actually have a similar energy content. So perfect. That looks perfect. So yeah, that's absolutely wrong. Their energy contents are similar. Next one, B, can be classified as a biofuel. Yes, it is. Sugarcane, because ethanol that is produced from sugarcane is classified as a biofuel. Because remember, for it to be considered as a biofuel, it needs to be replenished quicker than it's been consumed. Now, think about it. Sugarcane, you can grow for like 1 year and you can just keep growing it. Let's say it takes 1 year to grow. It's very easy to be replenished, whereas look at coal. Coal takes millions of years to form. So the big difference is the timing. So absolutely, sugarcane is renewable, hence it is considered as a biofuel. So I'm going to put a tick on that one. And let's have a look at the other ones. Let's see what the other ones. Just trying to see the other ones. All right. Cannot be used to generate electrical energy. Rubbish. Even though it's created from ethanol, like ethanol that's created from sugarcane, which is a biofuel, it's still ethanol. It's still, able to be combusted and hence be used for energy. It doesn't matter where it's coming from. If it is ethanol, ethanol is ethanol. So it is going to be used for electrical, it can be used for electrical energy. So rubbish. D, produces no greenhouse gases. Wrong. Remember, ethanol produced from coal and, ethanol produced from sugar, they both produce greenhouse gases. Now you might kind of think, okay, well, isn't ethanol that's produced from sugarcane much more better than coal? Absolutely true, because remember, there is carbon neutrality. So when we're actually, let's say we're forming ethanol from sugarcanes, we're releasing carbon dioxide. when we're combusting it, and hence that carbon dioxide that's like goes out to the atmosphere is actually absorbed by photosynthesis by the sugarcane, and hence it's like this circular thing. But okay, so if it's circular, you might think, oh, then ethanol that's produced from sugarcane has no greenhouse gases. But remember, wrong. What about the water that it produces? Remember, water, the H2O, is also a greenhouse gas. So don't forget, a lot of students are forgetting they both greenhouse gas. The greenhouse gases are methane, water, CO2. These are the main greenhouse gases. So absolutely, it does produce greenhouse gases. So it has to be B. Beautiful. Question 2. In humans, the oxidation of which chemical is the primary carbohydrate energy source? Straight away, easy. It is glucose. You should straight away realize that. Now, remember, look at the wording here. Primary carbohydrate. So it has to be a carbohydrate and it's our energy source. Well, in humans, the word oxidation, so a lot of students just get confused when they're saying oxidation. It's another word for like combustion. Think of it like combustion. You're going to sometimes hear the word oxidation, like what's the oxidation of methane? It's another word for oxidation. What's the oxidation reaction for methane? Something like that. So, yeah. Now, let's have a look at why the other ones are wrong. So, we're talking about the primary carbohydrate. So, amylopectin, absolutely. Amylopectin is a carbohydrate, but be careful. So, if you look at it in your data book, I think it's in the data book, if I'm not mistaken. The structures are normally... Have I put them in this data book here? There it is. Amylopectin, which is basically a starch. You can see it's a starch. But the difference is it's a polysaccharide. It's basically glucose formed together. So let's say this is a glucose molecule. So this is a glucose molecule. It's basically glucoses, a formation of glucoses that are basically just bonded together. A list of them that are just bonded together. And it's basically branched. Remember that amylopectin is a starch that is branched. Something like this, basically. If I just draw this like that. It's like basically... It's a branched... like a branched carbohydrate. Whereas... Yeah, it's actually not a primary carbohydrate. Our primary, it comes from our glucose. Glucose is it is what creates cellular respiration. It's what creates energy, the energy that is used for our cells. And yeah, so that is our primary. Amylose is the same. Remember, amylose. Be careful of the word amylose. Amylose is just basically starch, but it's linear shape. So imagine it's this here, but only imagine duplicating this linearly. So it's still starch. It's still starch. It's not actually what do we call it? It's not our primary. So these are wrong. Absolutely. And glycerol, nope. Glycerol is just a backbone of formation of triglycerides. So rubbish. Now, it is important this year that you need to remember the formula, the actual equation, the combustion or the oxidation reaction of glucose, and it's very easy. So remember, it's a glucose molecule, so C6H12O6 in its aqueous state, reacts with oxygen gas, which basically forms there's 6 oxygen gases, 6 CO2 gas molecules, and 6 H2O molecules in its liquid state. This is the formation of the oxidation of our primary carbohydrate, which is glucose. You need to memorize this for the study design, so please make sure you memorize this. And yeah, remember, it is exothermic, because you got to remember that it's just a combustion reaction. Remember, this is your fuel, and the other stuff are normal. Like, when you combust, you react a fuel with oxygen and releases CO2 and H2O. That's what it is. So absolutely, that is it. So 2C. Question 3, let's have a look at this. A box of rolled oats provides the following information. So the nutritional information is given. Serving per package is 24. Serving size is 40 grams. So basically each package has a serving size of 40 grams. So average quantity per 100 grams. Be careful. So the serving size is 40 grams, but this is the information for 100 grams of quantity. So basically, protein's 13.3. Okay, these are all good. Which component of the breakfast cereals will contribute to the least energy? So the less energy, the most that doesn't create the most energy, when one serve is completely digested. Careful here. 1 serve, not 100 grams. So you don't want to use these information to calculate them. We want 1 serve. Remember, 1 serve is 40 grams. 40 grams is the per serving size. So how do we, how do we transform these to, because they're 100 grams, how do we transfer them into that 40 grams? Well, easy. We can actually use ratios. So let's look at ratios here. So think of it like this. I'm going to put 2 division signs here. I know that basically having 100 grams in 100 grams. So let's look at protein first. We know in 100 grams quantity, we have 13.3 grams of protein. Now, in a serving size of 40, how much protein is that? So I'll put X on the other side. And so now it's just basically algebra. So it's basically 40 over 100, multiply both sides by 13.3, and we get X. This is basically our formula. So putting that there, so 40 over 100 times 13.3, that gives me 5.32 grams. Done. And so it's just basically the same formula. Like, for example, if I wanted a fat, I'm just going to put the fat mass here, 8.5, 40 over 100, 8.5. Which is 3.4. The next one is 55.6. 55.6. So 40 times 55.6. That gives me 22.24 grams. Done. All right. So now we can actually calculate the one that releases the most least energy easily. So let's look at the first proteins. Now, proteins, if you go to your actual formula, where's our energies? We just had them here. So energies are here. There it is, foods, and the energies they release per kilogram. So let's look at proteins. Basically, proteins, for every gram, they release 17. So let's do that there. So if I multiply this protein here by 17, how much energy is this protein releasing? 5.32 times 17. They're only releasing 90.4 kilojoules. So let's do that also for the fats. So for the fats, it's multiplying it by 37. And for the other one, it's multiplied by 16 for the carbohydrates. Done. All right. So let's put that here. So 3.4 times 37, which is 125.8 kilojoules. The other one is 22.24 times 16, which is 355.84 kilojoules. So having a look at these, what do we see? Well, the one that has the least energy is actually the protein. It's the protein. You can see that it's releasing 90.4 kilojoules. And the one that's releasing, the macronutrient that is releasing the most is the carbohydrates. So, once it's complete, it's protein, of course, so it's not these two, because it contributes to the total of 19.4. That's what we got. So it is, choose A for 3A. Question 4. The equation for the complete combustion of ethane at standard laboratory conditions is shown. Given that the molar mass of carbon dioxide is 44 grams per mole, the combustion of 4 mole of ethane under these conditions would produce which of the following? So we want that first to calculate the mass of CO2 gas that's going to be produced and the volume of greenhouse gases. Now remember what I said. What are your greenhouse gases? It is CO2 and water. But be careful. This water is not actually a greenhouse gas. And why is that? It's because it's not in its gaseous state. It's in a liquid state. For it to be known as a greenhouse gas, it needs to be in its gaseous state. So the only actually greenhouse gas is actually that CO2 here. So let's try to calculate the first one. Let's calculate the mass of CO2. This one over here. This one over here. So we're just going to use molar ratios. Like to get the mole of CO2, it's going to be basically, what is it going to be? So to get the mole of CO2 is going to be 2 times the mole of the mole of ethane, which is 8. Done. So we have 8 mole. And so to get its mass of CO2, it's multiplying its mole by its molar mass, which they've given us is 44, which gives me 44 times 8, 352. So it's going to be not these two, it's going to be one of these two here. What about the volume of greenhouse gases? Easy. Well, we know that the only greenhouse gas is that CO2. So we already calculate the mole of CO2, which was 8 mole. So because we know it's at CLC, at standard laboratory conditions, we can use our N equals V over Vm formula. Remember, it is in your formula sheet. This is a constant. Vm is 24.8. So, and our N is 8 in this case, and we can calculate the volume of CO2. So 8 times 24.8, 198.4, which is actually B. Choose B as your answer. Looks good. Question 5. Which is a correct procedure to follow when using a solution calorimeter? After calibration, the heating coil needs to be removed from the calorimeter before use. What? Rubbish. You keep that heating coil. Why? Because you need to heat up you need to heat the water. Or you need to heat the actual whatever solution that you have. Remember that the heating coil is used because you use it to give a certain amount of energy. And that energy is used for calculations for the calibration factor and stuff. So the heating coil needs to be removed from the calorie before use. Look at the word before use. Wrong. You use it because it gives a certain amount of energy that you want to allow. It gives a certain amount of energy, so that's used to calculate the calibration factor. So we've already calculated the calibration factor, sorry. But it's used to give a certain amount of energy that's used for calculating the change in temperature and stuff. So absolutely wrong. You keep it in there. Do not remove that heating coil. You don't remove it, so rubbish. B, using the same lead stirrer and thermometer throughout the experiment. Absolutely. It's important to even use the thermometer. They had the same thermometer because let's say you have a thermometer that was great and then you replace it. Let's say you use a different thermometer, but it was not very accurate. So let's say it was quite, not the best. You are affecting your actual your results very badly. This creates random error, which is a problem. So it's very important to keep consistent equipment like the stirrer, lead, and thermometer. So actually, that's correct. Next one, C. Double the calibration factor if the volume of the liquid is doubled. Ooh, let's have a look at this. So let's say this is our calibration. It's actually quite small. Solutions. Okay, this look how it looks. And say you doubled the liquid volume. Say this much. You doubled it. Now, remember, look at the calibration factor. It's the energy over change in temperature. Now, think about it. Say we're given the same energy for all. So this energy is constant. We give the energy here, and we give the energy, the same energy here. What is the difference between these here? Well, look at this. It's actually easier to heat up this water. The change in temperature for this is going to be quicker. The change in temperature is going to be quicker because there's less water, there's less solution. So it's able to basically heat up quicker. Whereas compared if you double the volume and give the same energy, it will take very long. Now, if it is, the change in temperature is going to increase, but at such a slow rate. Now, yeah, so it's going to increase at such a slow rate. So, absolutely. But overall, the change in temperature, the temperature change for this is going to be basically lower than this. This is going to be higher because the change in temperature is going to be quicker because of the less amount of liquid. This one's going to be much slower, but it will be basically less change in temperature. Now, because you've increased that volume, you have a less change in temperature, So if you have a less change in temperature, you need to have a higher calibration factor. So double the calibration factor if the volume of the liquid is doubled. You don't double it. Look, be careful here. Now, what did we just say? There's no formula for this. You remember, it is going to increase. That change in temperature is going to increase, but it's such a slow rate. So the calibration factor is going to actually decrease in certain time. It will decrease slowly, but it will stay still. Whereas the calibration factor for this one is going to be basically decreased so much quicker. So using a double, it's just a little bit, there's no you can't say double. Yeah, the liquid's doubled, then double the calibration. No, apps doesn't make sense to double it. Half the calibration factor if the volume of the liquid is doubled. Rubbish, same as the other one. Yeah. So double the calibration factor if the volume of the liquid is doubled. Yeah, it wouldn't make sense. See, both are increasing in change in temperature, but this one's going to be at a higher rate. And it's basically a little bit less. So yeah, doubling it's not... That's not... It's still increasing. It's not like it's decreasing. It's still increasing. But yeah, absolutely doesn't make sense to double it. So choose B, I would say. Alright, 6. Miller performed the following experiment, added 120 milliliters of water to a clean, dry calorimeter, and monitored the temperature every 10 seconds over 100 seconds. After 100 seconds, apply a current of 1.8 amps over voltage of this and minutes of this, and then switch off the power, state the solution. So Miller's plot of the recorded temperature over the time is shown. Alright, using the information from the plot, the temperature change that Mia should use for the calibration is closest to what? Ooh, easy. Now, have a look at this. You can see that basically this is when, I think like 100 seconds is when they basically turn on the voltage. And so basically you can see that the temperature is rising. Like you can, let me use a different color. You can see the temperature is rising. Rising. And so basically around here, they shut off at like 400 seconds. They basically shut it off. But there's a big problem. Now, if there was no, if it was perfect insulation, there was no energy loss, it would have been like a constant from right there over there. But we can see that there's actually energy loss here. And then there's actually constancy here, which is perfect. There's constancy here. So to calculate temperature change that will be used for calibration, it's quite easy. So remember, it's your... So to temperature, it's what's your final temperature. Now, you wouldn't... So you would actually... Because look at these here. These here are very basically... It's a straight line, which is great. You can see that if I draw a straight line here through these points over here, it's nice, but because there's this slight variation, I'm going to a little bit increase it. It's not going to be like this constant, I want to say it would be like this constant straight line, that final temperature. It's going to say like that. I would just say it would increase a little bit because of this slight variation there, that decrease. So to make up for that, a little bit increases. And it looks like it's around like 28.3, around that. That's your final temperature. And your initial temperature was 23. So you minus these two here. So it would be like, I would say, I don't know, let's say 28.5. 28.5 minus 23, which is basically 5.5 degrees Celsius. So C. Now, I think it's a stupid question, to be honest, because it could also be D in other words, because it really depends on how you look at it. Like, you can actually just draw, if students don't take that into consideration, I think it will still be correct, because all these dots, basically, all these points here are perfectly drawn. So let's say another student could draw it like this, and then slight increase it. Yep, here it is, 28.1. So it will also give D. I think it's just a stupid question, because what they've done is they put it at so close to each other, which I think it's it's not great. So I would say C and D. Any of these would be found to be correct. I think just the question itself is written rubbishly, to be honest. It's not... Yeah, there's going to be a variation between students, and I think a lot of students know the concept, but just the graph is drawn really badly. So I would say absolutely I would choose both of them. But I think 5.1 looks much more closer to doing it again. So if I did it again, so if I draw that line right here, just passing through these, there it is. And a slight increase, there's only a slight increase because of the variation. So it is like around that 5.1, I would say. Because there's only like 3 dots that are basically out of it, decreasing, whereas these here are basically constant. So absolutely, I think D would be most correct. Like, I would choose D, actually. I would choose D. I would actually choose D, in other words. But I also think C is correct. So any of these I would think you would basically get the answer right. Yeah, just written very badly. 7. Let's have a look at this. Oxygen gas is bubbled through a solution of sulfurous acid. The relevant half equations for the spontaneous reactions are shown. All right. Oxygen gas is a more powerful oxidizing agent. It means it's strongly reduced than the sulfide ions. Okay, what is the balance equation for this redox reaction? Easy. Because we know the oxygen gas, this one, is a stronger oxidizing agent than this, it means it's actually higher. This one over here is higher in terms of the electrochemical series. Now, because it's going to be, of course, it's a stronger oxidizing agent, means it's strongly reduced. It means the electrons are going to be on the left-hand side. So it's going to be basically, this equation is going to be the same. Can you see how the electrons are on the left-hand side? So this one, when this one reacts, it's going to be basically oxidized. So it's going to actually be like, write it in the opposite way. So make sure the electrons are on the opposite way. So let's write the first one. So O2. I'm not going to write gassy and stuff, just a waste of time. So 4H plus 4 electrons gives us 2 orders. Make sure, so 2 orders. Then, make sure, like, reflect this here to get the electrons on the right-hand side. So H2SO3 plus H2O results in SO4, 2 minus plus 4H plus 2 electrons. Now, beautiful, we've got them perfectly. Now, just make sure the electrons are the same. So you know how there's 4 here? There's 2 actually here. So we need to actually double this whole equation here. So, like, this is going to be 2 of these. It's going to be 2 orders. There's going to be 2 SO4s. There's going to actually be 8 now H pluses, and there's going to be now 4 electrons. Now we can actually cancel stuff out. Like, for example, these electrons actually cancel each other out. What else cancels out? Oh, these 4 H pluses. There'll be actually only 4 left out here. What else? These 2 H2Os actually cancel out. And yeah, those are the only things that cancel out. So rewriting this whole thing, O2 plus 2 H2SO3 results us in 4H plus 2 SO4, 2 minus. Done. Which one looks like that? Alright, it looks like actually A. So yeah, 7A. Beautiful. Question 8. In the human body, the role of an enzyme in the esterification. Esterification is another word for condensation reaction. And remember, condensation reaction is where basically the bond is formed between two values. So it's when, it's another word for condensation. So of fatty acids into triglyceride is best described as a process in which the protein undergoes chemical changes and becomes inactive. Rubbish. Chemical changes. Remember, the enzyme. By the way, enzyme is just a biological catalyst. Remember, a catalyst doesn't get affected by, it doesn't get affected. It's actually used in the chemical just to increase the rate of reaction. And hence, it doesn't go any chemical changes. It doesn't even go physical chemical changes. It just, you use it and it comes out unchanged. It comes out unaffected. So it has no changes in it. Be careful with the wording here. Undergoes chemical changes? No, not even chemical changes. Provides the necessary chemicals for the reactions to occur. No. An enzyme does not carry any chemicals. The chemicals are already there. Just the enzyme is just like a piece. It's like just basically like, it's something that's used to just increase the rate of reaction, to make the reaction quicker, and it's not affected. It doesn't even carry chemicals. So yeah, absolutely. Just remember, an enzyme doesn't even carry chemicals. It's just used to increase the efficiency of the reaction, the quicker the reaction is. And yeah, it doesn't, basically, just be careful, it does not carry chemicals for the reaction to occur. Increases the rate of both forward and backwards reactions equally. Now, it's true, yes, it does increase the rate of both forward and backwards, but the wording equally really is wrong. That really is something that, no, they're not equally, that's rubbish. The word equally really creates some uncertainty in this question. So it does make sense that it does increase both from rate and backwards, but equally not true. It wouldn't increase it both, forward and backwards equally. D, provides an alternative pathway that lowers the activation energy for the reaction. Absolutely perfect. That's the definition of what a catalyst does. And remember, an enzyme is a biological catalyst. Beautiful. Question 9. A reversible reaction. So this has an equilibrium constant of this at a given temperature. At that temperature, a particular closed vessel of fixed volume contains a mixture of SO3, SO2, O2 at equilibrium. And so 1 mole of O2 is added to the equilibrium mixture and the temperature is kept constant. At that instant that O2 is added, the frequency and success of collisions between SO3 molecules increases. Now just be careful with the wording here. It's talking about the frequency and success of collisions. Nothing got to do with equilibrium. So do not even touch Le Chatelier's principle. Do not even touch it. So we're talking about the frequency and success of collision. So think about it. If you've increased the oxygen gas quickly, if you increase the oxygen gas, so you put more, because there's more molecules of oxygen gas, they're going to be able to collide more. So at that instant, we're talking about at that instant, by the way. at that instant. Because you've basically increased oxygen gas, like you just basically put oxygen gas, now there's more oxygen gases and so molecules, and so basically if there's more successive collisions between those oxygen gas. And because they are both reactants, that SO2 and oxygen gas, they're going to basically collide with each other at that instant. They will be likely to collide with each other compared to this SO3. Now, because these will collide, they will form SO3 in some time given, like given some time, not at that instant, in some time given, and then SO3 will have more, collisions. But in that instant, oxygen gas will, the molecules will increase, and hence more collisions and successive collisions will occur between these two over here, because they are both reactants, I would say. Choose C. So, yep, oxygen gas, SO2 molecules instantly increases. Beautiful. Done. Next question. Question 10. Which of the following concentration time graphs best represents the equilibrium system when the system is below heated? Well, let's think about it. It's an exothermic reaction. So energy is going to be released. I'm going to write E, energy. So think of that energy as just a molecule. So if you're heating, like the actual system, you're increasing this energy over here. And so think of it as a molecule. By the Stallin's principle, if you increase that energy, the system's like, oh my God, there's too much energy on the product side. I need to find a way to get rid of it. So what it's going to do, it's going to go favor the backwards reaction to get rid of that excess energy. And so what would happen? Well, think about it. Now we know this, this whole thing out. What's going to happen is the reactants are going to increase, whereas the product is going to decrease. But because there's only one product, we should just see like one line going down, and two of those lines should be going up. So let's have straight away B is wrong. Just be careful. B is wrong. When you're doing a temperature change, there's no instant increase in concentration. Be careful. It's slowly like this. It's actually slowly, not at an instant sharp point. So B is wrong. So yeah, we said that there should be two lines increasing. So this one's increasing, that's good. And this one's increasing, great. So it could be that one. We could put a tick on that. What about C? Nope. Two things are decreasing and only one's increasing. There should be two increasing. So C is wrong. D, this one's increasing and this one's increasing. Beautiful. So two are increasing. Could also be D. So it could only be between A and D. Now look at the hint is actually this here, the coefficient of 2. Well, B is actually going to be increasing twice the amount compared to A because it has 2 moles of it. So have a look at these two here at A. These are wrong because they're increasing at the same rate, basically like a 1-to-1 ratio. Whereas at D, you can see that this one's actually doubled compared to this one. So this one with D is actually your right answer. And that double is that B. So this would represent B, this would represent C, and this would represent A. Perfect. 10D. Question 11. The equation for the decomposition of dinitrogen tetroxide is this. The value of the equilibrium constant for this reaction is this. A sample of this is added to an empty container of a fixed volume. The system is then sealed and heated to 200 degrees Celsius. After a certain amount of time, both gases are analyzed and the concentrations are found to be this and that. It can be concluded that the reaction is at equilibrium. The backwards reaction is to be favored to reach the equilibrium value because Q is less than K. So all the questions are talking about Q, which is the reaction quotient. And remember, the reaction quotient actually is such an important tool because it's able to tell us where the reaction is. Is it favoring the backwards or the forwards reaction? And where it wants to move to go towards that equilibrium. And remember, just the reaction quotient is easy. It's just a formula for your actual, your normal, equilibrium constant. So it's going to be, looking at this, it's going to be NO2 squared over N2O4. And that's going to be what's NO2. So for these ones, so it's going to, and remember, the difference between the reaction quotient is that you can use it for any point, so at any point in time. Compared to the equilibrium constant has to be at equilibrium, precisely at equilibrium. But the reaction quotient can be used at any time to see if it's reaching equilibrium, to see where the reaction is going, is it going backwards or forwards. So NO2 is 2.4 mole, being all squared or being divided by 0.4. So that's going to give me 2.4 squared, 0.4, which is basically 14.4 mole. Done. So we got the reaction quotient now. Let's have a look at this. Let me just rub this out. So we got the reaction quotient, as this over here. Now what do we see? Well, we can see that the reaction quotient is less than the actual equilibrium constant. And what does that really tell us about the reaction? Well, think about it. If the reaction quotient, remember the reaction quotient is trying to go towards that K value. It wants to go, so remember how the reaction quotient for this case is 14.4 and it's less than that 36. What the reaction quotient wants to do is go reach that 36. So what it has to do, it has to increase. So the reaction quotient is trying to increase itself. And for it to increase itself, it needs to basically, think about it. So remember the same as, it's like the, it's basically this formula. I just kind of rubbed it out, but let me write it here. So the reaction quotient is NO2 squared into O4. Now, for the reaction to increase, what has to increase? Well, of course, the numerator has to increase, but the denominator must be decreasing too. It must decrease for Q to increase. And so what does that tell us? It's a concentration of NO2, which is basically the product's increasing. So it's actually favoring the forwards reaction. Because when it's favoring the forwards, it's creating more of that NO2, and it's actually decreasing the NO2 forward, which is what this is telling us. So basically, it's favoring the forwards reaction. Okay, so A is wrong. They are not at equilibrium because they had to be equal, but they're not. Q is less than K. Backwards reaction needs to be favored to reach the equilibrium. No, remember we said forwards. So choose C. Forwards reaction needs to be favored to reach equilibrium because Q is less than K. Done. Concentration of both gases will need to increase for the system to reach equilibrium. Rubbish. Only the NO2 will have to increase. The other one has to decrease. So choose 11C. Question 12. An alkaline solution is electrolyzed to produce hydrogen and oxygen gas. The half equations for the reactions occurring at the anode in this cell will be what? Remember, the anode is where oxidation occurs. Oxidation. Okay, so we know oxidation. And also we know it's an alkaline solution. So basically it has OH ions. Not H plus ions, H plus for acidic solutions. So let's have a look at, well, do all of these have actually OH ions? Yes, this one does. So this could be also, this looks great. Nope, not this one. This has H plus, which is acidic, rubbish. And this one also has OH. This looks good. Now remember, this is anode, which is oxidation. And for oxidation, we know that electrons are always on the right-hand side. So looking at this here, electrons are on the left-hand side, rubbish. B, electrons are on the right-hand side, great. We could put a tick on that. D is also wrong because electrons are on the left-hand side, not right-hand side. So your only possible answer is 12B. Question 13. In a particular recharge battery, the overall equation for the discharge reaction is shown below. The polarities of the cathode during the discharge and recharge are what? So cathode is positive, cathode. Okay, so what do we, I think this, I'm just going to go in very detail with this because I think a lot of students do get confused because they think that, well, let's have a look at it. Let's actually analyze this. Well, we know that the cathode, let's have a look at the cathode. Your cathode, and this is your anode. Let's have a look at this when it's a galvanic cell, so that actual discharge reaction. What do we know? Well, we know the cathode is where reduction occurs. Reduction. Anode is oxidation. Reduction, oxidation, and having a look at this, what does this tell me? Well, we know at the cathode during recharge, it is a positive, and at discharge, recharge, it is negative. Looks like B is our answer, so 13B. 14. The structure of a new drug, which is hoped will be effective against infection, is shown. Which of the following correctly names the circled functional groups labeled X, Y, and Z on this molecule? Okay, well, let's have a look at this circle. Beautiful, this is an amine. Amine. Remember what an amine looks like. Amine looks like this. It looks like this. So C, we have N, and we have HH. So you can see that it's bonded to one carbon, and that carbon's normal. See this here? This carbon's normal, and it's bonded to an NH2. Be careful, it's not an amide. An amide, the carbon that is bonded is, basically, it has an oxygen in it, and then it has an NH. That's the big difference between these two. So this is an amide, not an amide. This is the amide. Right over here is an amide. You can see that this carbon is bonded to the double oxygen here. The oxygen here. And so then we have an NH here. What about this one here? What about Y? This is a ketone. Remember, what does a ketone look like? It's always occurring in the middle of a structure. It looks like this. This is just a C double O. Done. Next one is just a nice alcohol. Done. So amine, ketone, alcohol. Let's have a look. X is what? Of course, it's a amino, not amide. Take those off. Y is a ketone. Is it a carboxyl or a carbonyl? Now, of course, ketone is not carboxyl. Carboxyl is like carboxylic acid where it has a C double O OH. Not like that. It's a carbonyl. It only has a C double O. So it's this one over here, and then hydroxyl. Beautiful. D. If you're actually wondering, you're like, what the hell? How do I know the difference between these two? Well, one of the best ways is you can actually look at it in your formula sheet. Like if you come here to your data book, so going to naming compounds, I don't even remember. There it is here. So for example, the one that we just did was amine first. So where's amine? Here. It's known as amino. So that's why. The next one we said was ketone. Carbonyl. And that's where it is. What about alcohol? Where is alcohol? Hydroxyl or hydroxy. Any of these. So there it is. So it's D in that case. All right. Let's have a look at the next question. Question 15. The correct IUPAC name for the compound shown above is what? Easy. So first we need to look at the highest priority functional group. And we can see, what is it? It's actually this ketone here. This ketone right there. And then of course we have the bromine here. But ketone, because the one that, there's a kind of a trick to know which one has the highest priority. If it has more oxygens, then it has higher priority. Because you know how a ketone has oxygen here? It's actually the highest priority. And so now we also need to count how many oxygens there are, like in terms of chain. And we can see that there is 1, 2, 3, 4, 5. There's 4, so it's a pentane. And where does that, because you know our highest priority is a ketone, it occurs at the second carbon, so it's pentane 2. And how does that ketone end? It's on, I think, if I'm not mistaken, on. And you can double check that using your formula sheet because it's actually, your data book. So there it is. A ketone ends up with a on. So it's a pentane 2 on. And where does that bromine occur? So 1, 2, 3, 4. 4 bromo. It'll be in front of it will be 4 bromo. Perfection right there. So it has to be that. So 4 bromo pentane 2 on. Which looks like D is our answer. 16. Which of the following molecular formulas represents a straight chain fatty acid containing the greatest degree of unsaturation? So the one that has the highest degree of unsaturation. What is the degree of unsaturation? This is actually new in the study design. Well, the degree of unsaturation, so the degree of unsaturation basically tells us the number of the carbon-to-carbon double bonds plus the actual cyclic, cyclic, cyclic rings, cyclic rings. So it tells us like the number of carbon-to-carbon double bonds, but also how many cyclic rings, the number of cyclic rings. For example, benzene, or what about, cyclohexane. These are all rings. And so it also tells us how many rings there are. Now, we don't actually have to worry about cyclic ring in this case because it's actually a straight chain fatty acid. So we don't actually have to worry about that. So basically, when we're trying to calculate, in this case, the degree of unsaturation, we're actually just calculating the number of carbon-to-carbon double bonds. Which of these molecules actually has the highest carbon-to-carbon double bonds? How do we do that? There is a formula, the degree of unsaturation formula. It's such an easy formula to know. So the degree of unsaturation formula works like this. It's basically the number. It is the number, so the number of hydrogens. So it's the number of hydrogens if molecule was an alkane minus actual number, so minus your number, so hydrogen, so number of hydrogens actual I mean, I'm making up this formula, but I know what it is. So so let me just, so I will explain this is the best formula to use here. Actual, all divided by 2. Let's explain how we use this formula over here. How can we use it? This is the actual, the degree of unsaturation formula. For example, let's try the first one. So we can see that we need to first calculate the number of hydrogens if it was an alkane. Remember the alkane formula? It's CnH2n plus 2. So we need to calculate how, if this molecule was an actual alkane, how many hydrogens would there be? Well, we can see that there's 10 carbons. So imagine putting that N, it's 10. So how many hydrogens would be there? So it'll be 2 times 10, which is 20, plus 2, which is 22. So there's actually 22 hydrogens. So we can put 22 minus, what is the number of the actual hydrogens in this molecule? It's actually just 16. And then you divide this by 2, and you basically get 3, meaning that this here actually has 3 carbon-to-carbon double bonds. How easy. And we just keep doing it. Like, let's try to do it with the other one. Same thing. So the actual number of, hydrogens, if it was alkane, so it'll be like 12 times 2 first, which is 24, plus 2, which is 26. And then you divide this, then you minus it by the actual number, which is 22, and you divide that by 2, which is just 2. And you just keep doing that and see which one has the number of the highest degree of unsaturation. Next one is just basically 16 times 2, which is 32, plus 2, which is 34, minus 32, and divide that by 2. That gives you 1. Yes, so 1. Just has only 1 carbon-to-carbon double bond, and the other one just the same. So 18 times 2, which is 36, plus, so 38 minus 34 divided by 2, and that gives you 2. So the one that has the highest degree of unsaturation is actually A. So choose A as your answer. Beautiful. I hope you guys enjoyed this video and learned something through this video. Please make sure to like and subscribe for more future videos. And yeah, I hope you guys enjoyed the video, and please take care of yourselves. Bye bye.